So I had a request that there are some new team members or people who may not have had a chance to see the proposal or discuss the proposal. And today I would like to go through what the proposal says we plan to do. Um, this will be our science objectives and mission design. And uh, on August 28th, if you're typing and not on mute, now is a good time to mute.
It looks like Simon Wing is typing and is not muted.
Oh, Simon. That's better. On Friday, August 28th, NASA announced that 5 out of 13 proposed MidX proposals had been selected for $1.25 million Phase A studies. And those 5 proposals were Solaris, led by Don Hassler, Muse, led by Bart DePontiu, Helioswarm, led by Harlan Spence, ARCS, led by Christina Lynch, and Storm, of which I'm the PI, and that's what I'd like to talk to you about today. So one of our jobs is to distinguish ourselves from these other missions and show the advantages of choosing us. So please put yourself in that frame of mind for this presentation. For those who are not scientists, this is an imaging mission. And there once was a time when I was a student at UCLA in the atmospheric science or meteorology department, as it was called then. And it was our daily pastime to try to predict weather at UCLA in Los Angeles on the basis of whatever was happening in the Pacific Ocean. There were no satellite images, and all that we had was a NOAA ship, and it was called Ship P, and it was stationed in the Gulf of Alaska. And its job was simply to sit there and report what weather it was observing. So if you forecast weather in UCLA, you're supposed to try to do it on the basis of observations by a single ship in the Gulf of Alaska. That's one way to do business. But very soon after I came to UCLA, the GOES satellites were launched, and they took infrared images, and you could immediately see fronts or structures moving across the Pacific Ocean towards Los Angeles. You could even deduce whether they were cold or rain producing. So these images made a dramatic change in our ability to understand weather on the surface of the Earth. And so will the images that STORM conducts make an advantage to understand space weather in the vicinity of Earth's magnetosphere. This is the cover of our proposal that was submitted on STORM. And on the left, you see an outline of things I'd like to discuss today. One is the mission design. The second is the payload on the spacecraft. The third is the science that STORM will conduct. The fourth is briefly STORM and you. And at the bottom is further reading and contact points. So one of our selling points, which the review panel got, was that STORM will conduct end-to-end science. The mission studies processes that occur at the dayside magnetopause on the side of the magnetosphere that faces the sun. It images the location of the magnetopause. It images the auroral oval, and it images, at least remotely, and perhaps remotely, the processes that are occurring in the magnetotail, and it images the injections of particles from the tail into the inner magnetosphere. And finally, to complete the cycle, it looks at the effects of the ring current back on the magnetopause and the ring current back on the magnetotail. So we follow the flow of energy from the dayside magnetopause across the polar cap into the magnetotail, then deep into the inner magnetosphere, and the effect of energy deposition deep in the magnetosphere on the aurora, on the magnetopause, and back on reconnection in the tail. Okay. Good. So now I'd like to talk a little bit about launch and orbit. The spacecraft is launched directly into an orbit that ultimately goes out beyond lunar orbit. How far it goes beyond depends on the phase of the moon, because the intention is to go out and catch the moon back on the inbound portion of that orbit and use a lunar assist to get up out of the ecliptic plane into a high latitude orbit. and then it will be coming back in towards the Earth. It takes about 7 days to get back towards a 30 Earth radii orbit around the Earth. And when we get close enough, the spacecraft has to brake, and then we enter this big circular orbit with a radius of 30 Earth radii and a period of 9.65 days, which stays fixed in inertial space. And from that big circular 30 RE orbit, we look down upon the Earth from above, but also below, and also from the sides, and all latitudes and all local times with our imagers. The orbit is so big that we can observe the solar wind for much of the orbit, and therefore we can observe our own input into the system in situ, the solar wind magnetic field and the solar wind plasma, and we can observe the response of the magnetosphere in soft X-rays, in far ultraviolet, and in ENAs, and we'll talk more about that. Oops. So it's a 2-year mission, nominally, with a 90-degree plus or minus 10 inclination orbit, a 9.65 day period, a 30 plus or minus 1 RE circular orbit around the Earth. The instruments all have high heritage, and here they are. The one that I've been associated with is in the upper left, and it's a soft X-ray imager. This particular instrument is being refurbished to go sit on the lunar surface right now, and it will be going up in 3 years to the moon. JHU APL supplies an ENA imager, which measures energetic neutral atoms. UC Berkeley provides the FUV camera to look at the auroral oval. Goddard can provide a magnetometer here, a long history of that, and Southwest Research Institute will supply a plasma instrument to look at the solar wind. For reference, if you've not been associated with the mission long, the lead for the soft X-ray instrument up here is Scott Porter at Goddard. The lead for the ENA instrument at JHU APL is Pontus Brandt. The lead for the FUV auroral imager is Harold Frey at UC Berkeley. The lead for the plasma instrument, which measures the solar wind, is Phil Valek from Southwest Research Institute. And the lead for the magnetometer at Goddard Space Flight Center is Michael Peruker. Northrop Grumman is our excellent partner for a spacecraft bus, and we will use the very high heritage Leo Star 2 spacecraft for this mission. We have a dedicated array of ground observatories. These observatories are auroral all-sky imager cameras in the red and green lines, looking up from 14 locations spanning Western Canada, Central Canada, all the way to Alaska. These cameras are in red and green lines to observe spectra of the aurora and to observe their spatial variations at a very high resolution, much higher than can be achieved from space. And the lead for that is Xiaoyan Xie at JHU APL. Further beyond those, there's a contributed instrument on the spacecraft. We talked to Shingo Kamedo of Rikyo University in Japan. He had flown the Lyman Alpha imager shown here on the right side of the picture on the unsuccessful Procyon mission. It was an asteroid flyby mission, but fortunately on its way out to the asteroid, it turned back to look at the Earth, this dot in the center, and it measured Lyman alpha emissions from the Earth's neutral exosphere, the outer atmosphere of the Earth, surrounding the Earth at many, many radii from Earth. This instrument, the observations from this instrument can be used to determine the variation in neutral density of the Earth's atmosphere as a function of distance from Earth, latitude, and longitude. So that is a contributed instrument. Preparing this talk made me want to think about the history of soft X-ray imaging. It's an unusual instrument for magnetospheric physicists. So I have a brief history of how we got involved in this instrument. long before I was thinking about space physics or instruments or missions. In 1979, there was a paper that described a technique by which you could build wide field of view imagers for grazing incident soft X-rays. Prior to that, soft X-ray imagers had very narrow fields of view. That was back in 1979. That idea wasn't put into use for a long time, but it was a pioneering paper. The soft X-rays only make grazing incidents, but on these square pore, slumped, micropore reflectors, you can focus them down onto a detector plane and improve the performance. So that was back in 79. Not so much happened until 1996, when astrophysics instruments were turned to look at comets. And to their surprise, the astrophysicists found that comets emitted soft X-rays. So one conclusion you might draw from that is that comets are so hot that they emit radiation in soft X-rays, but that would be the wrong conclusion to draw. Comets are not so hot, they're actually very cold. Nevertheless, they emit soft X-rays. And the solution to that problem was provided by our team member Tom Cravens in 1997, who realized that these were line emissions of soft X-rays. And these line emissions are caused when a high charge state solar wind ion meets a neutral atom. They exchange electrons. The high charge state ion captures an electron, but it's in a high energy state. And as the electron decays, it gives off a line emission of X-rays. That's back in 1997. Things stayed for a while. In 2001, our same co-I, Tom Cravens, realized that it might be possible to see soft X-rays coming from Earth's near vicinity. He looked at Rosenet observations of soft X-rays with IMP8 solar wind flux and found that one tracks the other. And so what that means is that somewhere in the near vicinity of Earth, there is something that is emitting soft X-rays due to charge exchange, and that the emission rates depend on the solar wind flux coming into the Earth, the solar wind plasma flux, the flux of high charge state solar wind ions, for which he took as a proxy the flux of solar wind protons. He set his graduate student, Ina Robertson, to work trying to simulate what these emissions should look like. And in 2003, she published a paper which showed they should be most intense from the subsolar region just outside the magnetopause. That's because that's the region where the solar wind plasma is most compressed as it flows in from the sun on the left towards the Earth. Earth is hiding behind this magnetic barrier, which is the magnetopause. The solar wind plasma is compressed and has high density there. And it's also the place where that plasma gets deepest into the Earth's exosphere. So there's the most plasma there, and there's the most neutral atoms. So that's the best place to produce soft X-rays. So we knew that in 2003. And then it was realized a few years later in 2006 that some of that solar wind plasma actually comes down the cusps and gets very close to Earth. Not a lot, so the density of solar wind plasma may not be high, but the density of neutrals there is extremely high. And because the densities of neutrals is high, that's actually a bright emitter of soft X-rays. So there's only one movie in this presentation, and that's this movie. And this movie shows you what an imager might expect to see, a soft X-ray imager, that's over here, when the IMF turns from northward to southward. So what's going to happen when the solar wind's magnetic field turns from north to south, reconnection is going to begin on the dayside magnetopause, that's here, and reconnection is going to move the magnetopause closer to Earth. And so you're going to see this boundary move closer to Earth, but you're going to see it in soft X-rays, so it's going to move closer here. As the magnetopause moves closer to Earth, it moves deeper into the exosphere, and the emission intensity is going to increase. So let's see if that happens. Here it comes. Up, the boundary is moving closer to Earth, and the emissions are getting brighter, and in particular, they're getting very bright in the cusps, which means a lot of plasma is getting into the Earth's magnetosphere during periods of southward IMF. So I'll show that one more time. Here comes the southward IMF turning. Whoop, reconnection happens, everything moves earthward, plasma starts getting into the cusps, the magnetosheath brightens in soft X-rays. That was understood back in 2006. My involvement in this activity doesn't even begin until 2007, when my colleague, deputy for this mission, Michael Collier, came by my office and asked me, "Hey Dave, what would you do if you could image the magnetopause?" And I thought about that for a while, and then I asked him, "Why are you asking me this question?" And that's how I got involved. Meanwhile, other people were much more engaged than me. Scott Porter, the lead for the X-ray instrument, submitted to NASA a mission concept for putting an instrument on the moon. That's now coming true in only 3 years from now. Brian Walsh will put an instrument on the moon to look back at Earth. And they decided that the moon was a great vantage point because it always faces the Earth, and therefore that'd be a good place to view these soft X-rays. And colleagues in the United Kingdom looked at XMM astrophysics observations and found they very frequently saw soft X-rays coming from the subsolar magnetosheath, which indicated that those emissions are almost always present. Probably the single biggest step forward came in 2010 when Jerry Goldstein, a colleague on this mission's proposal, proposed an explorer mission called MAGIC. MAGIC was a multi-imaging mission. Unfortunately, MAGIC didn't win, but the success of MAGIC was to spur us onward, to get us to keep working, to get all of us to keep working and keep trying on it. And over the succeeding years, we did a lot of background work. In 2010, Michael Collier published an article in EOS, which was recognized in Science, which described the advantages of soft X-ray imaging, and that got us some publicity. In 2012, our English colleagues proposed a low-altitude mission to look up at the cusps in soft X-rays. They didn't succeed, but more recently Brian Walsh has, and next year he will launch a low-altitude mission to look upward and see the cusps in soft X-rays. And our colleagues Michael Collier and Scott Porter and Kip Kuntz began working with astrophysicists to conduct sounding rocket flights, which would carry a prototype soft X-ray imager. In 2015, another prototype imager flew on a rocket flight. It was a CubeSat with a soft X-ray imager. Europe and our colleagues in Britain and in China proposed the SMILE mission, and it was actually selected. It carries a soft X-ray imager, an ultraviolet imager, a magnetometer, top hat plasma into an elliptical orbit, and is currently scheduled to fly in fall of 2024. Walsh proposed the Cupid CubeSat back in 2015, and it's going to fly next year into a low altitude orbit and look up at the cusps. After many years, we finally got around to publishing a definitive paper on soft X-ray imaging in 2018, and last year, we proposed this proposal, which has gathered us all together, and Brian Walsh's instrument for the lunar surface was selected. It'll go up in 2023. So that is some idea of how long we've been working on this and what happened to get us to this point. But back to the general topics of STORM, it's expected that STORM will observe the solar wind input because it's on a high radius orbit and spends a lot of time in the solar wind. It will image the magnetosheath, the magnetopause, and the cusps. It will image the auroral oval. It will image the plasma sheet and ring current, and it will image the Earth's exosphere, and that's what I'd like to talk about now. These are the locations of those targets. The solar wind is out here. We'll observe it coming in with the in situ measurements, the magnetometer, and the plasma instrument, IES. We will image the dayside magnetosheath, which is region just outside the magnetosphere, image the cusps, image the aurora in FUV, image the plasma sheet in ENA, image the ring current in ENA, image the magnetopause in soft X-rays. Modeling is extremely important to this mission. Modelers help us predict what we should observe, but they also help us interpret what we will see. And we have several modelers on our team. We have people who use the BATS-RS model. It's a global magnetohydrodynamic model. It tells you where the magnetopause and cusps are. It can be used to tell you what's precipitating into the ionosphere. The same is true for the open GGCM model. It's a global magnetohydrodynamic model. The CME model studies the Earth's ring current and helps us understand what's happening deep inside the magnetosphere. That's something to be imaged by the ENA instrument. There are various exospheric neutral density models. They help us understand the Earth's neutral atmosphere, how far out it extends, and what density it has at different radial distances. And there are also various combinations of magnetospheric plasma models, MHD models, and ion models inside the Earth's magnetosphere. Oops. So what are the sorts of things that you might expect to see with real observations from the different instruments on STORM? Well, our plasma instrument and our magnetometer will expect to observe the solar wind input, and here we've rather boringly assumed that the solar wind plasma density is absolutely constant at 10 per cubic centimeter, but that there's a step function southward turning in the interplanetary magnetic field. This should initiate exciting things in the magnetosphere because a southward turning of the interplanetary magnetic field causes reconnection on the magnetopause, causes the magnetopause to move, adds magnetic flux to the magnetotail, adds magnetic flux to the polar cap, causing the auroral oval to expand, ultimately results in activity in the magnetotail that sends bursts of particles into and feeds the ring current. So the soft X-ray imager will observe X-rays. Where's my pointer? We'll observe, I don't see a pointer anymore, but in any case, oops, the X-ray imager will observe in the left on the bottom.
I'm in the middle of a meeting, but what do you need?
So Stephen, you're not muted.
Sorry.
Okay. The soft X-ray imager will observe emissions from the magnetosheath, and that's what's shown in this colored crescent on the left on the bottom. And from that, you can pick out the magnetopause. You can also pick out the bow shock. The auroral FUV imager will observe electron and proton emissions from the auroral oval, which can help you determine the size of the oval and whether there are transient events. The ENA imager will observe the ring current, but not only the ring current, like image, but also will observe ENAs emitted from the near-Earth plasma sheet. So we can study something about the plasma sheet from the side on, and that's what this figure shows. And the array of ground-based all-sky observatories can take pictures that can be pieced together to give you very detailed structure of the auroral oval as a function of latitude and local time. Here's our Leica instrument from Japan, once again observing the neutral density cloud of the exosphere around Earth. From the emission intensity, you can deduce the profile of neutral densities as a function of latitude, longitude, and radial distance from Earth. That's very useful because the neutrals plus the ring current produce ENAs, which is an ENA instrument observable, and the neutrals plus solar wind ions produce soft X-rays, which is an X-ray imager observable. Let's see if we can make it go on. It was important to us to show in the proposal that we knew what backgrounds these images had to be extracted from. For example, beyond the Earth's magnetosphere is what astrophysicists study, soft X-rays from locations far, far beyond the Earth. There are some places in the sky above the poles which have more intense emissions. There are some places near the equator where the background soft X-rays have lower emissions. Similarly, the Lyman alpha sky has variations as a function of longitude and latitude. ENA observations must be detected against a UV background. and the far ultraviolet images of the auroral oval must be distinguished from dayglow or other sources of emissions. But there's no particularly bad place in the sky to look, and so we expect to observe observations from anywhere we go along our orbit. What might be an ideal observation for the STORM mission? Well, it might be a southward IMF turning observed by the magnetometer, that's this step function here, at a time when the solar wind plasma is absolutely constant. And then we would know that any change in the magnetosphere was directly attributable to this southward IMF turning. And one such change we'd expect in the magnetosphere is that the southward IMF turning would initiate reconnection on the magnetopause and cause the magnetopause to erode quickly and then slowly inward. This is actual output from a global MHD model, and the model suggests that reconnection initially moves the magnetopause sharply inward and then more gradually over the course of an hour. The magnetopause recovers and moves back outward following a substorm in the night side magnetosphere, at least according to this model. And checking this model is something we'd like to do. When the southward IMF turning occurs and there's reconnection on the magnetopause, it should remove magnetic flux from the dayside magnetosphere and add it to the polar cap. Consequently, the amount of flux or the size of the polar cap should increase with time at all times when reconnection on the dayside exceeds reconnection in the tail. Once reconnection occurs in the tail, the substorm goes off, magnetic flux is returned to the dayside magnetosphere, and the auroral oval should shrink again. If you were to look at the location of the auroral oval as a function of local time, midnight, 6 a.m., near local noon, the motion of the oval will depend on what local time you're at, and how far it expands will depend on your local time too. Those are all observables for the FUV imager, which can tell you where the auroral oval is. Meanwhile, down on the ground, using the all-sky imager cameras in the night side sky, we should see the auroral oval expand. That means move further from the pole. That means increasing co-latitudes of the auroral oval until that substorm goes off, at which time it should contract back upwards abruptly and shrink, and there might be subsequent motion. And all these detailed structure that you see here, those are observables for the all-sky camera, and they're potential substorm triggers. And finally, when the substorm goes off, it should inject particles into the ring current, and here are some predictions from a ring current model. Substorm, IMF turned southward, magnetopause eroded, polar cap expanded, substorm went off, ring current ions were injected from the magnetotail into the ring current, perhaps in 2 steps here, and that is an observable for the ENA camera, the flux of ring current ions as a function of time. Oops. So in the big picture, MMS, you may have heard of, is a mission with 4 very closely spaced spacecraft that tell the microphysics of reconnection. That's what's shown here in the bottom left figure. It's an exceedingly important topic for space physics and for magnetospheric physics because, strangely, processes that occur on microstructure in space physics can affect the entire system. And so it's absolutely crucial to understand what's happening on the smallest possible scales, on the scales of electron and ion gyro radius. And that's what MMS does. Somewhere in between are other missions like Themis or Cluster or Van Allen probes. But way up here on the big scale has hitherto not been studied, and that's what STORM does. STORM is exactly the opposite of MMS, studies the same problem, reconnection, particle acceleration, but it does it by taking global pictures of the system, the entire dayside magnetosphere, the entire ring current, the near-Earth plasma sheet, the entire auroral oval, to see what's happening on global scales. Going back to the 4 topics I mentioned at the beginning of this presentation, this mission studies reconnection at the dayside magnetopause. It studies the response of the magnetotail to varying solar wind input. It studies the growth and decay of the ring current in the inner magnetosphere. and it studies the means by which the inner magnetosphere has feedback upon the magnetopause or upon the magnetotail. So in the first topic, magnetopause reconnection, the tasks for STORM are to determine the different kinds of reconnection modes on the dayside magnetopause. Is it steady? Is it unsteady? Is it localized? Is it extended? Where does it occur on the magnetopause? We know from empirical studies that the dayside magnetopause moves inward when the IMF turns southward. That indicates reconnection is happening, but we'd like to know how fast or how slow, whether it occurs steadily or in jerks. And the way you'll do that is by finding the magnetopause in images and tracking how it moves as a function of time. As a corollary, the far ultraviolet camera will observe the auroral oval and see how the auroral oval moves as a function of time. To conduct that task, you have to know the solar wind input. That's why we have a magnetometer and a plasma instrument to tell us what are the input, what is triggering, what is driving this motion of the magnetopause. And if you want to evaluate the significance of reconnection, you'll do it by determining the amplitude of that magnetopause motion, the amplitude of the auroral oval motion, the amplitude of the cusp motion. So one would anticipate, again, measuring the input, measuring the solar wind plasma input, measuring the magnetic field input, looking in the images and marking off boundaries for the magnetopause. For example, here, the Earth is here, the magnetopause is here, the bow shock B is here, marking off those boundaries, marking off the boundaries of the auroral oval, marking off where the ring current is, and then tracking them versus time. Marking them, like here with that X, and comparing them with the predictions of different models. Models in which they move fast, models in which they move slow, models in which they move steadily, models in which the boundaries move in step function. If you could mark off where that boundary is as a function of time, you would be able to pick out which model is the correct model for that particular set of circumstances. In this case, I've put the X's down on the dotted line, showing that things are happening steadily, but very gradually, and the magnetopause boundary is moving slowly inward, following a southward IMF turning. The second science topic for the mission is magnetotail reconnection, and here the idea is to distinguish or discriminate between the different kinds of magnetotail response modes, which include steady magnetospheric convection, isolated substorms, sawtooth or repetitive substorms, substorms that occur during the course of geomagnetic storms, to go back to our own solar wind observations and look for triggers, to look and see if there's any evidence of triggers in the magnetosphere, such as oxygen in the magnetotail, and to quantify how often these different modes of magnetotail response occur and quantify how significant they are to the overall interaction. To conduct this task, we'll need both the far ultraviolet camera looking down on the auroral oval and the all-sky imagers looking up from the ground into the nighttime sky. We'll need the magnetometer and the plasma instrument to determine the solar wind occurrence patterns and look for triggers. We'll need the far ultraviolet imager to see just how much open flux there is in the polar cap, ENA to look for evidence of oxygen or to determine plasma sheet thickness, which might be a trigger for substorms. We'll need the all-sky imagers to look for streamers and auroral beads. Gosh. And we'll determine the significance from how the flux changes and whether the magnetopause and cusp rebound outward in response to these night side events. There is an enormous array of possible magnetotail responses in the literature. This is a partial list of them. Each of them requires a different combination of storm imagers to identify. Identifying how often and under what conditions they occur is an objective. Determining their effect on the flux in the polar cap determines their significance. Let's see if we can go on here. Whoops. So, for example, Larry Lyons and colleagues at UCLA have proposed this all-encompassing picture of what happens following a southward IMF turning. Magnetic field lines are peeled off the dayside magnetopause. sink into the magnetotail where reconnection occurs and pushes them back to Earth. That's 1, 2, 3, 4, 5, 6, 7, 8. That is some feature moving across the polar cap, 1, 2, 3, 4, 5, 6. That is some feature brightening on the night side auroral and pushing things back around the sides to the day side. So the sort of things you might see in that are a feature begin near the day side and extend towards the night side, trigger the onset of a substorm in the high latitude night side auroral oval. See that feature stream or spread towards lower latitudes, brighten, causing substorm onset. The auroral oval shrinks but brightens. That's one possible sequence of event. That's one mode of magnetospheric response. That's what some people believe happens. A consequence of substorms and night side activity is that particles are pushed deeper inside the magnetosphere into the ring current, and you would expect different quantities of particles and different energization to occur in response to steady magnetospheric convection, isolated substorms, sawtooth storms, substorms, and storm substorms. Our task is to identify which of those adds more particles to the inner magnetosphere, and it's also to determine how particles are lost from the ring current. Possible loss mechanisms include magnetopause outflow, charge exchange, or wave-induced precipitation into the atmosphere. This picture over here on the right shows a comparison of anticipated soft X-ray images, that's the yellow and red, which we would use to pick out where the magnetopause is, and anticipated ENA images of where ENAs are being generated. And in this particular picture, the ions are drifting this way, that's these contours here, and they're reaching the magnetopause and they're being lost to the magnetosheath. And that's why there are more ENAs coming from the post-noon magnetosphere than the pre-noon magnetosphere. The combination of the X-ray imager and the ENA tells us where the magnetopause is and tells us where the ions are coming from and suggests that those ions are being lost by hitting the magnetopause and leaving the magnetosphere. So there are different combinations of instruments. The far ultraviolet imager and the all-sky imager help us define the magnetotail mode that's happening. The energetic neutral atom imager observes injections and ring current variations. It observes dawn-dusk asymmetries in particle fluxes. The XRI imager observes the magnetopause location, and the far ultraviolet imager observes precipitation of these particles into the auroral oval. So we have the observations we need to quantify sources and losses of ring current ions. To complete the global cycle of science, we want to determine the effects of the ring current back on the magnetopause and back on the magnetotail. And in particular, we'd like to know whether the ring current has an effect on substorm occurrence in the tail and whether it has an effect on magnetopause location. The reason it might is because, like its name suggests, the ring current is a current circulating around the Earth, and it produces northward perturbations at the magnetopause, which should push the magnetopause out by pressure balance, and it should produce northward perturbations in the magnetotail, which should inhibit the occurrence of substorms. So to check if that's going to happen, we'll need to look at ENA observations to track ring current intensities. We'll need to look at the far ultraviolet observations to observe substorm onset and open up and how much open polar cap flux there is. And we'll need the soft X-ray imager to determine the magnetopause location and motion. So we had to show that we're related to heliophysics, and indeed we did, because we said we distinguish between and quantify reconnection modes at the magnetopause and in the magnetotail, and we study particle acceleration mechanisms in the near-Earth magnetotail. Innovation is a key word with Thomas Zurbuchen and with our colleagues at NASA headquarters. I welcome your suggestions and improvements to ensure that our mission is regarded as highly innovative. STORM is in an unusual and interesting, highly inclined circular orbit from which it can obtain global images from all perspectives. It's a self-standing mission that can take its own measurements of the solar wind input. It has no perigee pass, so it can observe continuously through 1 to 3 day geomagnetic storms. It has its own dedicated array of ground-based imagers to look at the auroral microstructure. It has a novel soft X-ray imager to track magnetopause and cusp motion on appropriate timescales. And the ENA instrument extends down to thermal energies so that we can look at substorm effects in the magnetotail plasma sheet. This shows a comparison of the timescales that could be studied by previous missions and STORM. Simply by sitting up there in its 10-day orbit, STORM can observe throughout the course of geomagnetic storms everything that's happening from a variety of perspectives. So each imager, each instrument on STORM has a particular task. The soft X-ray imager should look at the magnetopause and cusps. The far ultraviolet imager can see the auroral oval and its boundaries. The ENA imager can look at ENAs from the ring current and plasma sheet during geomagnetic storms and substorms. The plasma and magnetic field instruments measure the solar wind input. Leica looks at the exosphere in Lyman alpha, and the ground-based all-sky imagers look at the auroral microstructure. And those instruments are used in different combinations to address the various tasks that I've talked about here. All of the instruments are essential for some of the tasks. All of the instruments are needed for full mission success. The science data products are what you might expect: plasma and magnetic field parameters, soft X-ray imagers from which you can pick out the magnetopause and cusp locations, auroral images to look at the size and dimensions of the auroral oval, its brightness, its variations, ring current images of ENAs, of the plasma sheet 2. Leica is going to tell us the neutral density as a function of radius and local time and latitude. And the all-sky imagers will tell us the microstructure of the night side auroral oval. It's our intention to have an open data policy and rapid data dissemination. That is something that has benefited Themis, the mission I've most associated with in the past. It persistently enables them to be a partner with all other missions and ground-based observatories. These are the names of some people you may hear come up in your deliberations. Michael Collier is the deputy PI for this mission. Gerald Delmans is the formulation manager helping us prepare the Phase A proposal. Juan Raymond is the mission system engineer. Charles Baker you may have met during the Step 1 proposal. Charles is still available for consultation. The instrument system engineers are Zach Fenn and Conrad Schiff. You've probably met and talked with them at this point. Our proposal manager is Tanya Hines-Watts. Our financial lead is Chris Grau. We are looking for a payload manager, and we have 2 cost volume managers, Yolanda Scott and Venetia Mason. Storm and you, this is how we go out and talk to other people. Storm provides context for all magnetospheric missions and many ground observatories. Storm helps GDC. Storm works closely with global simulations. We absolutely welcome partners in all of these communities. We hope to attract lots of interest as we go through Phase A. I'm delighted to be working with all of you. Each of you is hereby appointed an ambassador to represent our mission. Most importantly, I'd appreciate comments, suggestions, and especially criticism to improve our proposal. We've been told repeatedly that headquarters is seeking breakthrough science and innovation. The more you can help me articulate that, the better our chances are. Here are some papers for further reading. We have a website. It's at www.stormmission.com. And these are my email address and Michael Collier's email address. And I'd be happy to take any questions from anyone on any topic or to initiate any discussions between any combination of people who've on the phone. That's the end of this presentation. Thank you.